These are the answers to the Chapter 7 packet, Periodic Properties of the Elements. Section 7.1, Development of the Periodic Table. In 1869, Dmitri Mendeleev and Lothar Meyer organized their periodic tables on the basis of increasing atomic mass. Why didn't these scientists choose to arrange the elements in order of increasing atomic number? Well, in 1869, the concept of atomic number was unknown to scientists. This is before they had discovered that the atom has a nucleus. Mendeleev is generally given credit for discovering the periodic table, even though he and Meyer had very similar arrangements. The likely reason for this is that Mendeleev had the courage to leave blank spaces in his table to make room for elements that he predicted should exist but had not yet been discovered. Two elements that were called Eka aluminum and Eka silicon are located directly underneath aluminum and silicon on the periodic table. So underneath aluminum is gallium, underneath silicon is germanium. In 1913, Moseley's work developed the concept of atomic number. So looking at two specific elements on the periodic table, iodine and tellurium, the average atomic mass of iodine is less than that of tellurium, and yet iodine is placed to the right of tellurium. And again, this is not because of atomic mass, it's because of atomic number. So because the atomic number of tellurium is 52 and that of iodine is 53, then iodine, which has one more proton than tellurium, should be to the right on the periodic table. All right, looking at page 46 in your textbook, under the section on basic forces, we read on page 46 that the magnitude of the electric force between two charged particles is given by Coulomb's law. So force equals a constant times Q1 and Q2, which are the magnitudes of the charges on the particles, and then divided by d squared, where d is the distance between their centers. So what does that tell us? Well, it has to do with attractive forces if it's a pair of oppositely charged particles, or it's repulsive forces if the charged particles have the same charge. Coulomb's law describes the magnitude of the force between two charged particles. This force is directly proportional to the magnitude of the charges, Q1 and Q2, and this force is inversely proportional to the square of the distance between them. Again, opposite sign, those are attractive forces. The same sign, that would be repulsive forces. The attractive force between an electron and the nucleus depends on the magnitude of the nuclear charge and the average distance between them. So as nuclear charge increases, the attractive force increases. As the electron moves farther from the nucleus, the attractive force decreases. The net electric field created by the nucleus and the electron density of the other electrons is called the effective nuclear charge and symbolized by Z with the subscript EFF. In a many electron atom, the inner or core electrons partially screen the outer electrons from the attraction of the nucleus. The effective nuclear charge increases from left to right across any period of the periodic table, but going down a column, the effective nuclear charge is pretty much the same, and it changes far less than it does across a period. All right, section 7.3, sizes of atoms and ions. We can define the atomic radius as half the distance between the two nuclei of bonded atoms, and within each group on the periodic table, the atomic radius tends to increase from top to bottom as you travel down the group. This trend results primarily from the increase in the principal quantum number of the outer electrons as you go down a column. Within each period on the periodic table, atomic radius tends to decrease from left to right. And the main reason for this trend is the effective nuclear charge increases across a period. So in this particular table, we are comparing two elements and deciding which one is going to have a larger atomic radius. So the comparison between sodium and potassium points to the fact that potassium should have a larger atomic radius because 4s is larger than 3s. We're talking about the valence shell. Comparing aluminum and silicon, we would say that aluminum should have a larger atomic radius because silicon has one more proton than aluminum, and those outer electrons are in the same 3p subshell. For sulfur and fluorine, that's a little bit different because they're not in the same period or the same group, so they're along the diagonal. But we know that sulfur should be larger than oxygen, and oxygen should be larger than fluorine, so therefore sulfur is larger than fluorine. Now, if we go the other direction and try to compare oxygen and chlorine, we can't do it just based on periodic trends. So even now, looking on page 257 in your book, with the extra information in front of us, it turns out that chlorine, the atom, is slightly larger in size than oxygen, the atom. So 0.73 and 0.99, I believe those are in units of, I think it's angstroms, but anyway, the unit's not really important. All right, so now that we know that chlorine is larger than oxygen, remember, I would not make you compare two elements that are located along that particular diagonal because it's just not possible to know for sure which atom is larger. All right, still in section 7.3, part E, when a cation is formed from a neutral atom, electrons are removed from the valence shell. The ionic radius of a cation will always be smaller than the atomic radius of its parent atom. On the other hand, when an anion is formed from a neutral atom, electrons are added to the valence shell. And because of the increase in electron-electron repulsions, the ionic radius of an anion will always be larger than the atomic radius of its parent atom. All right, when comparing ions that have the same charge in the same group, so as you're going from top to bottom, the ionic radius increases. This is because the principal quantum number of the outermost occupied orbital of the ion is increasing. A group of ions that contain the same number of electrons is called an isoelectronic series. If we compare two or more ions that have the same number of electrons, the ion that has the largest effective nuclear charge would be the one that has the smallest ionic radius. So to arrange these 5 ions from smallest to largest, first we have to decide if they have the same number of electrons. And these are 5 ions, 4 of which are isoelectronic. So 4 of these ions all have 10 electrons, but one of them has 18 electrons. So the 18 electron ion should be larger than any of the 10 electron ions. All right, let's find out who has the largest effective nuclear charge. Which one has the most protons in that set of 10 electron ions? Well, magnesium has 12 protons, sodium has 11 protons, fluorine has 9 protons, and oxygen has 8 protons. So in that order, that would be from smallest to largest. And then finally, we know that the sulfur ion has 16 protons. All right, so magnesium 2 plus is the smallest, and then sodium plus, fluorine minus, oxygen 2 minus, and then finally sulfur 2 minus. In section 7.4, ionization energy, we define the term as the energy required to remove an electron from the ground state of a particular atom, and it's typically done in the gaseous state. The value of ionization energy is often measured in kilojoules per mole. The greater the ionization energy is, the more difficult it is to remove an electron. Now we're looking on page 259 at table 7.2, and the first question that we're asking about these successive values of ionization energies is why do they tend to increase for a given element? And the answer, as you can see on page 259, is that with each successive removal of an electron, we're now pulling an electron away from an increasingly more positive ion. So that means that it's going to require more and more energy to remove a negatively charged electron from a more positive ion. Now, looking at the data, it says that after we remove the valence electrons, there is a sharp increase in the value for ionization energy when we get to the core or the inner shell electrons. So the reason for this is because the core electrons are located in an orbital that is much closer to the nucleus than the outer shell or valence electrons. And since the core electrons experience a much greater effective nuclear charge, it's going to require a much greater amount of energy to remove them. The inner core electrons are very tightly bound. Therefore, when electrons are shared or transferred in chemical reactions, only the valence electrons are involved. The first ionization energy generally increases as we move from left to right across a period. And as we move across a period, the effective nuclear charge increases and the atomic radius decreases. So thus the electrons are more attracted toward the nucleus of the atom. The first ionization energy generally decreases as we go from top to bottom down a group. As we move down a column, the atomic radius increases, while the effective nuclear charge increases rather gradually. In general, the smaller the atomic radius, the higher the first ionization energy will be. The energy required to remove an electron from the outermost shell depends on both the effective nuclear charge and the average distance of the electron from the nucleus. Now we have to explain why there seems to be a little bit of a change in the trend in that boron, which is further to the right of beryllium, actually has a first ionization energy that is slightly less than that of beryllium. So you might think, well, how can that be? Since boron should have one more proton in its nucleus, why is 801 less than 899? What's going on? Well, think about where that electron is coming from. The electron to be removed for boron is coming from a 2p orbital, but the electron to be removed from beryllium is coming from a 2s orbital. So the valence electron for boron occupies the 2p subshell, whereas in beryllium, the 2p subshell is empty. So if it is slightly higher in energy, if the 2p is higher than the 2s, it's going to require just a little bit less energy to remove the first electron from boron as compared to removing the first electron from beryllium. We also have to explain a slight decrease in the ionization energy for oxygen compared to nitrogen. And again, oxygen has one more proton than nitrogen, and yet 1314 is a little bit less than 1402. Well, if you look on page 261, they say that the decrease in ionization energy when moving from nitrogen to oxygen is because of the repulsion of paired electrons in the p4 configuration. So the idea is that those two electrons that are occupying the same orbital in the p4 configuration of oxygen, there is a little bit of repulsion making that electron slightly easier to remove. When electrons are removed from an atom to form a cation, they are always removed from the orbital that has the highest principal quantum number. For example, in lithium, which is 1s2, 2s1, the electron that is lost comes from the 2s orbital. When an atom of iron loses 2 electrons to form a +2 ion, so the configuration of iron would be argon 4s2 3d6. The electrons are removed from the 4s orbital. And if you have another electron removed, then that would come from the 3d orbital. If there is more than one occupied subshell for a given value of n, so for example, if you have like 2s and 2p, the electrons are removed from the orbital that has the highest value of L. So if I have a choice between taking electrons from 2s and 2p, I would take them from 2p first because of the higher value of L. Electrons added to form an anion, so for example, like oxygen gaining 2 electrons, they are added to the empty or partially filled orbital that has the lowest value of n. Now we're on to section 7.5, electron affinities. Is removing an electron from an atom an endothermic process or an exothermic process? Well, the first ionization energy of an atom is the measure of the energy required to remove an electron. That's an endothermic process. So the positive ionization energy means that energy must be put in to the atom to remove the electron. But electron affinity is the opposite of that. We're not taking an electron away, we're actually adding an electron to an atom. So the electron affinity is the energy change that occurs when an electron is added to an atom. So here we can see chlorine is gaining an electron to become the chloride ion. Oh, and look at that. It's not an endothermic process. For chlorine, it actually happens to be an exothermic process. Electron affinity is defined when a chlorine atom acquires an electron, energy is released. What does this information tell us about the relative stability of the chlorine atom and the chlorine ion? Well, if you're releasing energy, that must mean that the product, in this case the chloride ion, is more stable and has lower energy than the chlorine atom. So sometimes the electron affinity will be a negative number, as we saw for chlorine, but the electron affinity for certain atoms is a positive number. So for noble gases, it's positive. Think about this. Argon is already a stable atom. Adding one more electron is going to make it unstable. So for some elements, like noble gases, the electron affinity has a positive value, meaning that the anion that's being formed is unstable or higher in energy than the original atom you started with. All right, moving on to section 7.6, metals, nonmetals, and metalloids. Metallic character generally does something as we go down a group and as we go across a period. If you're not sure what exactly is metallic character, let's take a look on page 265 at this figure 7.12. So increasing metallic character is happening from right to left and from top to bottom. So metallic character increases as we proceed down a group, and it decreases as we move from left to right across a period. Metallic character relates to the atomic radius and the ionization energy. Larger atoms tend to have low ionization energies because they tend to lose electrons easily. So a larger atom is going to be more metallic in character. As far as the physical characteristics that are going to be common among most metals, this is found on page 264. Metals are shiny, they are malleable and ductile solids, which means they can be hammered into thin sheets and drawn into wires. They are good conductors of heat and electricity, and a metal oxide is an ionic solid that is going to act like a base, and it tends to form cations in aqueous solution. So there's lots of metals on the periodic table. Metals tend to have low values for ionization energy, and they tend to lose electrons when they react, so they tend to become oxidized. What fundamental property of an element is the best indicator of whether it behaves as a metal or a nonmetal? Well, it's going to be the ionization energy. So the low ionization energy generally tends to refer to a metal. Metals react with nonmetals to form ionic substances. And again, metal oxides behave as bases, which can form metal hydroxides in aqueous solution. If a metal oxide does not dissolve in water, it should be soluble in acidic solutions because they will react to form water and a salt. Now we're supposed to write balanced chemical equations for various reactions. Here the first one is potassium oxide, which has the formula K2O, reacting with water. We're going to have the formation of hydroxide ions. So we get potassium hydroxide, and then the equation is balanced with a 2 in front of the potassium hydroxide. Copper Roman numeral 2 oxide would be CuO, and that reacts with sulfuric acid, H2SO4, and it's a double replacement reaction, so we get water and copper sulfate. Here on page 266 you can see examples of metal oxides and water to form metal hydroxides, and you can see examples of metal oxides reacting with acid to form a salt and water. Alright, well now on to nonmetals. It's going to be that they are not shiny, they are brittle, poor conductors of heat and electricity, and nonmetal oxides are going to form acidic solutions. And they tend to form anions or oxyanions in aqueous solution. So when nonmetals react with metals, metals lose electrons and nonmetals gain electrons. If a nonmetal oxide is soluble in water, it tends to form an acid in solution. And nonmetal oxides can react with bases to form a salt and water. So as far as balanced chemical equations, if SO3, sulfur trioxide, reacts with water, you're going to get some sulfuric acid, H2SO4. When diphosphorus pentoxide, which is P2O5, reacts with aqueous sodium hydroxide, NaOH, you're going to get water and a salt. In this case, the salt is sodium phosphate. So had P2O5 reacted with just water, you would have gotten phosphoric acid, H3PO4. But this is reacting with a base, so that acid gets neutralized to form a salt and water. Metalloids, such as silicon, have properties that are intermediate between metals and nonmetals, which is why they can be used in semiconductors. And again, going back to the last equation, I mentioned that P2O5 reacts with sodium hydroxide to produce sodium phosphate and water. And now you can see the coefficients. So the coefficients are 1, 6, 2, and 3. All right, moving on to examples of non-metal oxides. We have carbon dioxide, we have P4O10, tetraphosphorus decaoxide, and again reacting with water to produce acids or reacting with bases to produce a salt and water. And you'll find these reactions on pages 267 and 268. All right, section 7.7, trends for group 1A and group 2A metals. So alkali metals and alkaline earth metals. Alkali metals tend to have low densities and low melting points. The alkali metal of any given period has the lowest value for first ionization energy in that period. Lithium is going to react with hydrogen to make lithium hydride, which is LiH. Potassium will react with water to make potassium hydroxide, so KOH, and it also produces hydrogen gas. This is a single replacement reaction. Here are other examples on page 269 of alkali metals reacting with hydrogen, with sulfur, or reacting with water to produce metal hydroxides and hydrogen gas. Now compared with alkali metals, alkaline earth metals have higher densities and higher melting points. Strontium can react with water to form strontium hydroxide and hydrogen gas. Magnesium can react with barium, or is it barium reacting with magnesium? So one of these is not going to occur. Well, which of these metals is larger in size and therefore more metallic? magnesium or barium? Well, considering that barium is further down the column, as you go down, atomic radius increases. So barium is more likely to react and lose electrons than magnesium is. So the first reaction would not occur, but the second one you would just produce barium, nitrate, and magnesium in a single replacement reaction. And then finally, calcium plus nitrogen would make calcium nitride, and that equation is balanced, as you can see, with 3, 1, and 1. On page 272, you can look at alkaline earth metals reacting with water or reacting with nonmetals like chlorine and oxygen. All right, section 7.8, trends for selected nonmetals. How does the ionization energy of hydrogen compare with the other elements in group 1? Well, remember that hydrogen is a very small atom, and it's not really classified as a metal. So unlike the alkali metals, it is a nonmetal. And considering that there is only a single electron, it's a very small atom, the ionization energy of hydrogen is more than double that of any alkali metal. Here's some reactions of hydrogen. It will form a metal hydride, so potassium hydride. It will form hydrogen chloride. It will form ammonia, NH3. And calcium can react with nitric acid to produce hydrogen gas. It forms calcium nitrate and hydrogen, again in a single replacement reaction. What members of group 16, which is again the oxygen family, are solids? Oxygen is a gas, but sulfur, selenium, tellurium, and polonium are all considered to be solids. There are two different forms of oxygen. Those are called allotropes. We have O2 and we have O3. O2 is the more stable form of oxygen. Here we have a reaction that converts O2 into O3, ozone, and because the reaction is endothermic, it tells us that O3 is less stable than O2. As the atoms in group 16 become larger in size, they become more metallic in their properties. So polonium is a metal. The state of matter for the halogens are gas for fluorine, gas for chlorine, liquid for bromine, and iodine is a solid. Would the following reaction occur between bromine and sodium fluoride? Well, in order for bromine to replace fluorine, that would mean that bromine is more reactive than fluorine, but that's not going to happen. So bromine is less reactive than fluorine. Therefore, bromine cannot replace fluorine in a single replacement reaction. The order of reactivity for the halogens is that fluorine is more reactive than chlorine, which is more reactive than bromine, which is more reactive than iodine. So can fluorine replace bromine? Yes. Can fluorine replace chlorine? Absolutely. Can chlorine replace bromine? Yes. But bromine could not replace chlorine. Again, look at the activity series and you can see that bromine is less reactive, so it cannot replace chlorine. All right, the noble gas of any given period, so unlike the alkali metal that has the lowest value, the noble gas has the highest value for that particular period. And then our next little answer here has to do with xenon fluoride. So on page 276, they mentioned that back in the 60s, Neil Bartlett at the University of British Columbia was able to create the first noble gas compound, and that was a xenon fluoride compound, XeF2, so xenon difluoride, xenon tetrafluoride, XeF4, and xenon hexafluoride. So the possible products are a mixture of those three compounds. All right, well that wraps up the Chapter 7 packet. I hope that all of those answers were helpful to you. Thanks for watching.